Thank you. Thank you, Peter. Thank you. So thanks a lot for the invitation. It's really an honor being here. This beautiful city and beautiful site here. So let's talk about cement industry. Before I start about the cement industry, I have to talk about our company, since aixprocess is a rather small company. I don't assume you know it. So my boss wants me to show you this. So we were established in 2001. And as Peter mentioned, I joined the company in 2004, so I was the first employee, which I share with Peter, so we have a very similar history here. By now we are 18 engineers, mathematicians, and some software engineers also. We do a lot of CFD simulation. This is our main topic. So what you can see here, is Exergy. This is our daughter company. This is our face or brand towards the cement industry, but these are the same people. And we also have a shareholder. Lösche is a company doing cement mills. And this is one of the reasons why we are doing a lot of work in cement industry. So we have 3 columns of what we are doing. So we call it engineering services. This is about CFD simulation, data mining, and process design. And we also have what we call service solutions. This is the XPro-M online optimizer. I will get to that a little bit later. And solid sheet also. And we also design products, so we design cyclones and advanced flow equipment, and we also sell not only the basic and detail engineering, but the equipment itself, because a lot of customers asked us to provide the cyclone. So if it's not too big, then it's within our scope. We don't have manufacturing capabilities at our own, but we have companies we work with. So I will talk firstly about the CFD process simulation and what we do at aixprocess using Barracuda. So we are looking a lot at cyclones, not only for cement industry, but typically for cement industry, but also in power generation, CFBCs and something like that. So this is, I think you have seen a lot of these animations and a lot of these pictures before, so I don't have to get into detail. But we also look at circulating fluidized beds and typically how fuel is put into the fluidized bed, how the behavior at the bottom of the fluidized bed, how it's separated in the cyclones, and all these nitty-gritty details we are looking at and provide some expertise to our customers. If we are looking at a vertical roller mill, so this is the typical design for a cement mill. You will see that it has a lot of features built in. So it's one machine, but it's a whole process, branch of processes within the machine. So you have a comminution at the bottom. You have a pneumatic conveying of the cement towards a dynamic classifier. So you have internal recirculation. And you have a bed conveying here. So a lot of things are going on within these vertical roller mills. So to give you an idea, the largest mill provided by Lösche is about 8 meter in diameter and 25 meter in height, and has a throughput of 850 tons per hour. So these are really large machines and are hard to model because a lot of different processes go on in there. So we have this region with a very dense pneumatic conveying where we have to look at the distribution of the cement towards the classifier, and we can look at very detailed simulations here. And we have to combine several simulations to capture all this. So, but one of the most interesting parts in the cement process is the so-called calciner. Calciner is an entrained flow reactor where you have a lot of material pneumatically conveyed vertically, and you have also combustion and the calcination reaction. So To give you an idea about the cement process, it's a counter-current process. So the solid materials moves from up left to down right. So this is the entry of the so-called raw meal. It is injected to the cyclones, which we call preheater tower. Then it's calcined in the so-called calciner. It enters the rotary kiln, and then it's cooled and ejected as clinker. So the gas flow is countercurrent, so you use the cooler to preheat the gas flow. You have fuel into the kiln combustor, and this is the so-called tertiary air duct, and then you go towards the calciner and then separate the meal again. To give you an idea about the dimensions, a typical rotary kiln is about 70, 80 meters. I don't know the US numbers. Yeah, it's quite big. Yeah. Okay. So for the calciner, we have to consider the calcination reaction, which is highly endothermic. So you have to put a lot of fuel in there and burn it. And in the past, it was coal. And since cement is a very cheap product, everyone wants to replace coal with secondary fuels. So whatever has a calorific value is put in there. So I want to show you a case which we have done in the past. So it's a cement plant in Europe. Unfortunately, I can't tell you any details about it. It has a 4,500 tons per day clinker production, and it's a so-called semi-dry system. And the calciners are two-stage calciners where we have, this is just the end of the rotary kiln, and we look at the calciners, and they have some operational issues. So they have what they call pumping. So it's a frequent change of pressure during operation, which may be caused by material fall out into the tertiary air duct knee, but they weren't very convinced about that or not sure about it, if this is really the cause. They also have coatings and blockages in the bottom stage cyclone. So this means that they have a carryover of fuel and have afterburns in the cyclone. This is something you don't want to see here. And they also have CO limit exceptions, which is the most severe topic on this study. So the question is how to address this. Do you want to try it? And this is how it was done in the past quite frequently. So a lot of engineers with a lot of experience just know that from plant A it works, so it has to work for plant B. And as you mentioned in your talk, this is not working. If you have the same design, the same properties, it works still differently. This is true for the petrochemical industry, but also for the cement industry. So you have to be very specific on what you are looking at, and that's why we chose a model-based approach here. So for the model, we require quite deep insight into the calciner, so we have to look at a two-phase flow because the solids loading in the calciner is rather high, so we have to take this into account. We also have to consider the combustion to have the necessary energy, to have the necessary the correct temperatures and gas distribution, and we also have to have the proper velocities. Otherwise, we will not be able to achieve the right answers. And for that, we have to also consider the chemical reaction about the calcination, because it's not only endothermic, but it's always reduces the volume of the gas. And since we want to look at the emissions of CO, we have to consider that also. So we also have to consider different fuels. So as I mentioned, secondary fuels are used, but how to characterize this. So there are a lot of questions about drag and how to model that, and we need some verifications for this lumpy fuel or rubber band. This will behave completely different from a how you call a sphere. So we have to consider that. So we actually built this so-called zigzag zifter in an experiment, and we can introduce particles at the top and let them fall through this zigzag, and we have countercurrent airflow, and we take these experimental data and fit the model of Barracuda to it. And then we can use these settings to model the calciner. But also we have to consider particle shape, and since we also have quite large particles, fuel particles, we also have to consider a thermal shell model for these coarse particles, because assuming that the temperature is the same within the particle for these large model is not giving the right answers. So we have implemented thermal shell, so only the outer shell of the particle reaches the temperatures within the calciner and also is considered for the reaction. And we also have to look at the moisture distribution between within the particle. Is it only on the surface or is it homogeneously distributed within the particle? So this is some process details. I don't want to go into detail about this, but when we look at the first simulation results, we see that we have some meal storage. What is given here is the particle mass within the calciner over time. So you see this is a typical load phase, but then we have quite severe fluctuations. So these are up to 400 kilograms within some seconds, and this is what they see as pumping and fluctuation of pressure. So the result is what the operators see is pressure fluctuations, but also fluctuations in flue gas composition. So this means that we have not only insufficient pneumatic conveying within the calciner, but we also have a maldistribution, which means that the reaction doesn't take place or evenly of the cross section. So this is one topic, and we can, if we want to look at the reactions, we have the oxygen concentration on the left-hand side, and here is an isovolume of CO-rich regions. So this is explaining not only the pumping, you can see how it's fluctuating down here, but also you have a mild distribution about the cross section. And as the calciner is just up to here, everything which is carried over here for CO means that we have unburned fuel, and we still have combustion within the cyclone, which leads to coating and build up of layers you certainly don't want to have. So this is also caused by poor pneumatic conveying. So for the optimization, we had a lot of different opportunities or possibilities, but I want to show you just some simple ones. We had introduced a steeper cone, and steeper cone combined with a slimmer shaft, so to raise the velocities, which on the one side reduces the the time that is available within the calciner, but also reduces the pumping. So you have a more stable pneumatic conveying at the bottom. And to increase the time available, we also had an elongation of the calciner shaft and introduced a mixing chamber at the top. So from the operational view, this may sound as the most promising, but we also know that this is the most expensive revamp which has been done. This is why we try several different options. So here you can see the current scenario. The particles are colored by their species, so you can see how it is not very well mixed, and every now and then we have particles that fall through. And in the retrofit scenario, it's a much smoother operation. Of course, we have a longer time to have all the calcination done, and we also have no combustion afterwards. So what I like most about the study is that it is not only a study, it was really built, so it was realized by the third party, and after detail engineering and commissioning, they had the rebuild, and after that we see that all process issues were eliminated. So this plant is now running with the redesigned calciner for about 2 years. We could increase the capacity. Now the secondary fuel rate is at 100%. So this is one goal, and we still match the CO emission. So this is really a success story, and it was done. All the engineering was done up front, so there were no trial and error, and the duration of the stop was just 6 weeks. So this is a rather typical stop during summertime, where they do typically the revamping. So this is quite obvious that CFD really helps here to not trial and error at the field, but just virtually. Okay, if everything is so perfect with the CFD, are we still missing functionality in Barracuda? And as an engineer, we always have things to what we want to do better, and especially if you're based in Germany, you are really tough on that. So we would like to see more detailed geometry representation in Barracuda. I think this is a common request. Yeah? I really love the structured grid for the stability of the solver. A typical Barracuda run is just set up, let it run, come back for the results. And everyone who uses other CFD tools knows that this is not typical for CFD. So other CFD tools, you set up, you let it run, you rerun, you have to guide the solution towards a stable state, but this is not true for Barracuda, and therefore I love the structured grid, but it has disadvantages. We would like to see moving parts. There are a lot of solid mixers out there. I will show a classifier in a moment. So solid moved by a moving geometry would be great. And we would like to see heat transfer through walls. This would be a very common boundary condition. If you think about a combustor, you have temperature within, you have a layer of, let's say, insulation, you have metal, then insulation again, and you have an ambient temperature, which is typically known. This is an easy and very proper way to introduce a boundary condition, but still it's not possible in Barracuda. So I chose the dynamic classifier as an example because it has detailed geometries and moving parts within it. So if you are not familiar with classifiers, these are machines which allow to separate coarse and fine particles and classify them by having a rotating cage here. Okay, then we would also look at heat transfer through walls. The one example I gave you before, so I don't know why this isn't running. Okay, in this example we have a gas burner here, and then outside we have a fluidized bed system, but okay, the animation doesn't run, that's bad. So in this case, we had to couple these simulations using boundary condition on both sides of the wall. It would be much more convenient to have the heat transfer here. Okay. So all these examples have one thing in common. They are very detailed analysis, but what is if you are looking at the plant? So this is typical cement plant. It's quite complex. You could do this in a closed analysis, detailed analysis. It would take ages or years. So you have to put it in a series of separate analysis, but still these will be very detailed, and sometimes you just want to look at a larger scale. So we use solid sheet for that, and we can model all the cement plant within a flow sheet. This is MATLAB based, so it's rather easy to use, and we can use this for studying about where to put several units within your process, what is the most convenient. So in this example we just have different fan power and where to put the fan within the process and things like that. But you can go even further. You have a lot of data which is gathered within the process. This is a typical operator setup. So all these data are stored, but typically no one uses them. So we as a first approach, we took these data, and from acquiring the data, we had to build proper boundary conditions for the CFD simulations. But still, you can use the data itself because you have the data over a long time period, and you can see what happens within the process. So we can do some data analysis, some data mining here, and go through it and make some statistical analysis. We reduce noise and transform it and scale it, and then we can use it as a tool for itself. For example, here we can look at correlation matrix. So these are all channels that are used within the process. So let's say this is a temperature, and then you have pressure at the other side. And when you can see you have a large dot, so you have a high correlation. If the dot is small, you have a low correlation. So this gives you an idea of what process parameters really correlate to each other, and that hasn't to be on a process basis, but it's only a data basis. And sometimes this is really useful because operators, or let's say humans in general, don't have the ability to see relations between time-shifted process changes. So you can use this to give you an idea about what you are looking at. But also you can, if you have a multiple parameter sensor data, you have a multiple input and a multiple output problem. It is difficult to to optimize this in a natural way. So you can combine it with artificial neural net and have it run with a fast process model. So this can be a fast running CFD model or a flow sheet model. And combined, this is what we call XPRO-M. So this is, as mentioned before, brings the, let's say, the model world to the process back again towards the machines. So if you need all these additional data and additional models, is it still good to use CFD or not? Yeah. So I would like to cite a study from 2011. Why companies use CFD? So this is the top 5 challenges. So they have enhanced product complexity and want to understand what happens within there. They see that the performance of their products is affected by multiphysics. They have to verify product performance, and they want to operate at extreme conditions, which they can verify in an experiment. And they want to run multiple design variants there. So if you don't use CFD, you have to do more physical testing, and you have less scenarios you can test. You can also product operates, but is not optimized, and the troubleshooting is more difficult. So if you summarize this, you still need CFD, and you will even need CFD more, but it's not only CFD, you need all the different types of models and experiments also. So whenever your boss tells you CFD is too expensive, go ahead and show them why you still need it. Yeah. So here's a comparison between the best-in-class and industry standard and the not so good companies, and this is actual numbers given in this study. Okay, so when I have to conclude, all processes, including multiphase flow, are complex and dynamic. There is not one tool available to model all the processes, but from our experience, Barracuda VR is doing a fantastic job and provides really quick and very deep insight into these highly complex processes. And since we are using it now for about a decade, we really enjoy how Barracuda is developing and evolving, and we are using every single step and going ahead with it. Thank you.